As director of BU's Pardee Center for the Study of the Longer Range Future, Tony Janetos has committed himself to studying how changing climates affect policies across the globe. He has held executive leadership positions at organizations including the U.S. Environmental Protection Agency, NASA, the World Resources Institute, and the Heinz Center for Economics, Science, and the Environment. Tony also served as the co-chair of the U.S. National Assessment of the Potential Consequences of Climate Variability and Change. Please join me in welcoming Tony, who will speak on climate change and its impact on today's world and our future.
Okay, we good? Great. Beth, thank you very much. Good morning, and thank you for being here. Pardon me. I'm going to do several things today, and that's not what I wanted to do, actually. Sorry. I want to talk a little bit about context. Apparently, the other bullets have decided not to show up. My PowerPoint has not had enough coffee, I think. I want to talk a little bit about context. I want to talk a little bit about what we know about science, how we know it, and then I want to talk about what prospects are for the future and what kind of actions people are beginning to take or that we can foresee. So I want to just first point out the obvious. We are a coastal city. We are also a city of neighborhoods. So why does this actually matter? Why start there? It matters for several reasons. And one is that the global environmental changes about which we are rightly concerned have immediate local implications. They're not just for today, but for decades to come. That what we do today has a lifetime that will itself span decades, whether it's engineering actions, whether it's community actions. They're also quality of life issues for those of us who live here, for those of us who work here, and in fact for the entire region. And we really don't have the luxury to ignore what the facts tell us or ignore the experiences of others. There was a marvelous conversation last night for those of you who are here with the panel of mayors and elected officials. And Bob Oakes asked a really very unfair question at the end of the panel. You know, what do you do when you're confronted with skeptics? And there was a whole variety of answers, one of which at least I will not repeat. Yes, I can tell by who was here. You know exactly which one I mean. But there were all variations on a theme that Neil deGrasse Tyson has now made famous. The nice thing about science is that it's true whether or not you believe in it. And in addition, we need to recognize that we are collectively managing risk, even as we seek to understand more, that this is not simply a problem of trying to understand the way the world works, which is how most of us are trained, but we are in fact engaged in a larger challenge of managing risk. There's a very long history of how we know. For over 25 years in the U.S., the federal agencies, the science agencies of the federal government have collaborated on all the fields of climate science, and for the past 15 of those years have sponsored assessments of that on the state of the science regarding impacts in the U.S. that parallels the international scientific assessment process. So what I'd like to do over the next few minutes is talk about where we've been in that process and where we are now in our understanding. We've actually started with this very first report published on the eve of literally on the eve of the presidential election between Mr. Gore and Mr. Bush. So the nation was not exactly focused on its results, but even in this assessment 15 years ago, we established, I think, really quite clearly that there were substantial and important risks to a whole variety of sectors about which we care. Over the next decade, the U.S. Global Change Research Program published over 20 individual scientific assessments on particular sectors and issues of concern, and a few years after that, a second national assessment was done, which was a summary and a synthesis of all of those individual reports. Most recently, for the U.S., just last spring, a very large advisory group and hundreds of scientists and thousands of people around the country have participated in and have now published the third National Climate Assessment. And I'm going to draw on that for a lot of what I'm going to talk about this morning. And I'm going to start not by going through the litany of emissions, changing the atmosphere, changing the climate, impacting on resources, but I'm going to start with some of the bottom lines for the assessment, some of the major findings. And the first is that what we see in terms of the actual human-induced climate change and its consequences is no longer simply a set of modeling results for some time, decades in the future. We're seeing consequences now. Some of those consequences can very clearly be linked to anthropogenic, that is human-induced change. So this is an issue that is firmly in the present, not just for our children and our grandchildren. Secondly, even in this country, we are already feeling the effects of increases in some types of extreme weather, and in particular sea level rise and storm surge. This is a very clear pattern over the past several decades, and one that we are really quite certain about. Third, there are impacts in every region. Climate change doesn't occur in a uniform way, of course, across every region or in every season, but we are seeing impacts in health issues, in water issues, in agriculture, in the energy sector, in natural ecosystems, and more. But there are, in fact, things we can do. And we're beginning to understand what kinds of mitigation activities, that is the reductions in greenhouse gas emissions, or adaptation and preparedness activities that we can take either to reduce future change or to prepare for the impacts that we can't afford. Let me go back now, having talked about some of these bottom lines, and talk a little bit about some of the physical phenomena that we see. The world is indeed warming and changing. There are numerous independent lines of evidence about this. And of course, because our contribution to that is layered on top of a naturally varying climate, we don't have a uniform phenomenon of sort of equally rising temperatures across the globe or over time. There's still, it's not like it's the end of winter, right? We still have seasons, we still have hot years and cooler years, drier years and wetter years. But what we see over long periods of time looks something like this, where the colored bars are the deviations in global annual average temperature from the long-term mean, and the black line in the middle is what is one marker of what we've done to the atmosphere. This is CO2 concentrations, annual average CO2 concentrations. I actually started studying climate change for about the last 50 parts per million of CO2. I won't tell you how long that is. If you then look at this question of, well, it's a long-term phenomenon, maybe we shouldn't be looking at individual years, this is what it looks like per decade. The 1980s were at that time were the warmest decade on record until the 1990s, until the 2000s. And we're on track for this decade to be warmer still. There are numerous manifestations of this in the physical climate system. You're all familiar with this kind of depiction of the extent of Arctic sea ice. These actually come from satellite data. What the satellite data, on the other hand, don't show you, because all they're seeing, of course, is the top of the ice, is that at the same time as the spatial extent of the ice has decreased, it's also thinner. There's substantially less sea ice, and that you can only tell either by being out on the ice or from below through sonar measurements. We've also seen ice loss. So the previous graph doesn't really have an effect on sea level rise any more than the ice cubes melting in the drinks that you'll have at the end of the day at the reception doesn't affect the level of water in the glass. This, on the other hand, does. These are actually gravity measurements, again, from one of the NASA satellites that actually show that we're losing mass, we're losing ice from the grounded ice sheets. This does affect sea level rise. And it's pretty clear this is our doing. We're really the primary cause of these transformations over the last several decades. This, for example, is a marker of how we have begun to affect atmospheric composition. These are carbon emissions over the industrial age, from roughly 160 years ago to roughly today. And the striking feature here is what's happened after the Second World War. This dramatic expansion of it, these are simply the industrial emissions, by the way, not the land use emissions. This dramatic expansion of industrial activity globally, we're built on fossil fuels. I mean, our economies right now are built on this past history of burning fossil fuels. We can look at this another way, just in North America. These are data from 2010, as it turns out, that even while we have some sinks, right? We have growing forest, we've had sinks in agricultural soils, we've had a variety of other small sinks about which there's some uncertainty. Those sinks, in total, only add up to about 13 to 17% of the fossil fuel emissions coming out of North America. So we're, even on a smaller scale, just on our continent, we're already dramatically affecting the composition of the atmosphere and how the physical climate system itself works. And we're reaping what we sowed. Impacts are already widespread. If you look, for example, at this is just a simple picture of sea level, measurements of sea level rise in feet per century from the mid-Atlantic up to the up through New England. In this particular case, the largest rates of sea level rise actually are around the Chesapeake Bay and in the mid-Atlantic, with some of the largest rates around the Norfolk, Newport News, Virginia Beach area in Virginia, which also happens to be the site of the largest naval installation in the world. This is serious business and has attracted the attention of the people who are responsible for operations in that place. And we've seen, particularly in the West, increases in water stress, and in particular a sequence of what appear to be historic droughts in large parts of the western U.S. Not surprisingly, we also, in a sense, closer to home, closer to our pocketbook, to at least the pocketbooks of people around here, we've seen a number of other phenomena that go along with this. This is a graph showing the percent difference in heating demand from a long-term mean, actually the mean in this case of about the last 40, 45 years, where even though there's, you can see plenty of variation from year to year, we see over time this consistent decline in the demand for heating in the winter and a consistent increase in demand for cooling in the summer. We talked last night a lot about Hurricane Sandy, but before Sandy, there were Hurricanes Rita and Katrina. These were the paths, and this is emblematic of the way in which many impacts occur. It's not just the sort of slow response to a slow change in the climate system. The kinds of impacts that we actually see are punctuated. They're events. There are the consequence of changes in the statistics of extreme weather patterns and extreme storms and flooding. All these little red dots, by the way, were oil and I emphasize were, oil and natural gas platforms. Katrina in particular caused a significant interruption in both supply and production of natural gas from the Gulf. And even older assessments, in this case an assessment of risk to the transportation sector in the Gulf, showed significant risks from inundation and storm surge. This, by the way, I was on the advisory committee for this assessment. This was the scariest study I was ever part of, in part because the study was half done and then the storms hit. And about a year later, there was enough recovery of capacity for people to complete work on the study. So this was quite an experience. We know a lot from previous scientific assessments about effects on forests, effects on grasslands, effects on protected areas, agriculture, and so forth. Let me say a little bit about a sector that we don't often hear a lot about, and that's the energy sector. This is from one of the chapters in the National Climate Assessment. We don't often hear about it because I think the first wave of scientists who are interested in climate impacts all grew up as ecologists, and so we don't tend to think so much about the sectors like energy and housing and urban infrastructure. But it's clear that we're already beginning to see disruptions in energy supply and generation from extreme weather. We heard last night, in fact, about experience here in Massachusetts, which I hadn't known about, where during one of the recent heat waves, the ocean water that was actually used for cooling at Pilgrim Plant was too warm. There wasn't a large enough difference between the temperature in the ocean water and what was actually required to cool the plant. When that happens, and it's happened also in the southeast U.S. And in Texas a couple of years ago during their very significant heat wave, you have to derate the plants. You have to start to cut production because you simply can't cool in this case, either the reactor or in good old-fashioned coal-fired utilities. You can't cool the boilers fast enough or efficiently enough. We see seasonal change. I showed you the graph of cooling demand and heating demand. This is now a common pattern across the country. And this implications of less water, more periods of drought, punctuated by periods of heavy precipitation, which is really becoming quite a common pattern that we're seeing, especially in the Northeast, means that there are now times during the year, particularly in the summer and late summer, where we have to start dealing with the implications of less water for energy production. And of course, what we'll talk about all day long is sea level rise and infrastructure damage. Not just an issue for the East Coast. This is from a report from the Pacific Institute showing that even on the West Coast, there are power plants at risk from sea level rise. So what might the future hold? Well, in some sense, it depends on which future we choose. In the national assessment, we actually looked at two different scenarios, what we've called a lower emission scenario and a higher emission scenario. This is simply a depiction of what general circulation models have simulated about sort of which temperature trajectory we might be on. You'll notice that both of these, even in the lower emission scenario, is significantly warmer than today's world. If you then look at sea level rise, we look at past and projected changes in global sea level. This shows the continuity between old records, proxy records, tide gauge data, the more recent satellite data, and then what the future might hold. And the spread on the far right is composed really of two things. And one is scientific uncertainty. We don't know exactly where we'll end up. But the other is simply the consequence of a warming ocean. And of more melting of ice coming into the ocean. Interestingly, these results do not include the prospect of major destabilization of the ice sheets. This is largely thermal expansion and melting of landlocked glaciers. The international process has led to strikingly similar conclusions. In May, the Intergovernmental Panel on Climate Change published the Working Group 2 report. This is the report on impacts, adaptation, and vulnerability. And if you look around the world, and I promise not to go through every icon on this graph, but every icon is meant to show you, is to depict impacts in a different sector. And so really part of the lesson here is that there is no place around the world in which impacts from current change or projected change are absent. And this leads to the last part of what I want to talk about, and really the last part of what we talked about and wrote about in the National Climate Assessment. So this is one view of what we could do. I've shamelessly stolen this from the newspaper. But more importantly, there are opportunities to reduce greenhouse gas emissions or increase CO2 uptake. There are actions that we can take to prepare for impacts that are already unavoidable. The President's Science Advisor, John Holdren, has said there are three potential responses to climate change. You can reduce emissions, you can adapt, or you can suffer. We don't recommend the last. Some actions are already underway. So let me talk a little bit first, just briefly about emissions and mitigation. In fact, for the first time in the U.S. assessments, we had an entire chapter on mitigation, and I'll just share with you one of the main messages. And this is meant to give you a sense for the scale of the problem. This is a really hard problem to solve. CO2 right now is removed from the atmosphere by natural processes, by growing forests, by ocean uptake, at a rate that's roughly half the current rate of emissions from human activities. So think about this like a bathtub. The bathtub has water in it, and we have the faucet turned on so that water is coming into the bathtub, and there's a drain, but the drain is only letting about half the amount of water out that is coming in through the faucet. I shouldn't have to explain. That means the water level in the bathtub is going up, and you may want to think about calling the plumber. So one approach is, well, let's stabilize the emissions. But you know what? If you stabilize the emissions, that is, if you don't let the faucet, you don't turn the faucet up. Well, you just keep the faucet at the same level. This is not a good strategy in the sense that all that does is it limits the rate of increase. The water level in the bathtub, the concentrations of CO2 in the atmosphere continue to go up. They just go up a little more slowly than they might otherwise do. Same's true for other long-lived greenhouse gases. And so the magnitude of this problem is such that we not only have to stabilize emissions, we actually have to reduce them, and in the end, we have to reduce them very, very substantially over long periods of time. Restructuring the energy economy is a very, very serious challenge. The other approach about which we'll talk a lot today, of course, is adaptation, and here there's lots of local action. And I haven't even included the cover of Boston's own climate action plan. If you look across the country, there are many places where there are adaptation plans in place. And by executive order, there's now a sustainability plan for every single federal agency. And by executive order, they must consider the impacts of climate change and how they will actually begin to adapt to that. But are these plans effective? And largely, we don't know. They're too recent. We don't have a lot of real data for analysis about program effectiveness. There is this challenge of what I've called in a jargony way developing a counterfactual. What would happen had there not been an adaptation plan, which is a really quite a difficult analytical challenge. And what we do know in the research community is proving to be slow to penetrate private and public institutions in practice, and the converse is also true. What we know through experience and through experimentation in both public and private institutions has been slow to penetrate our academic institutions and research institutions. So where are we headed? We clearly need to evaluate where the scientific knowledge is moving and how that's changing. We need to keep track of progress on responses to climate change so that we, as we do periodic scientific assessments, at the same time we can do an assessment of how we're doing. It is important to keep your eye on the ball. The bridge is out ahead. And so let me finish. We're clearly seeing the consequences of changes in the climate system. You will almost never, I hope, hear a scientist use the phrase settled science. There's just simply a lot, but at the same time, there's a lot of what we do know that is simply not in serious question, about which there's a very strong scientific consensus. It's clear we have a very challenging problem of communicating. We like to talk about uncertainty and what we don't know. That's what makes scientists excited. Let's discover something new. But talking about what we do know and how well we know it is an unnatural act for many of us, and we have to get better at it. We need to acknowledge at the same time that the world is not going to wait while we sort out the things that we're not so sure about, and as we actually improve our knowledge about the physical world. And we need to keep remembering that we're managing risks as well as seeking to understand the world better, that this is really the very epitome of being useful as well as interesting. Thank you.